Orbit 9, 14, 872. Today we'll talk about their amazing robot that can do the high chamber, the high basket, and even climb very, very fast. It's the fastest robot I've seen in this event, and even more on Behind the Box.
Okay, so our main design based on a moving elevator on an arm, okay? We have our telescope here. It is our own custom telescope. It is made out of 35 by 35 millimeters tubes on 25 to 125 and 15 on 15. On each tube there is a 3D bearing that holds bearing that make the slide really smooth and stable, and also bearings on the bottom of each stage. It is wired by a continuous wiring coming from this dynamic rope that goes from this roller that's powered by those handball wheels that spin around each other and connected to 1,150 RPM motor. As you can see, it is a mechanism known from 2 keyboards last year. The handball wheels spin around each other. I'll move on to the arm. We have a new innovative mechanism that we didn't see first before. It's called a capstan mechanism. We basically have a low, I'll start with the gearbox. We have two 117 RPM motors that are connected to one gear with a 1:1:5 ratio. And they're moving this roller. This roller, it has a rope, it has a thread like that, like a screw, and the rope, it goes through it in a full cut, and then each side laps around the roller. And from and then each side of it goes to the higher roller. What happens is when the lower roller spins, one side it releases rope, one side it gives less rope, and it basically spins around. What's nice about it is that the rope can spin because it slaps around the roller, but makes the capstan principle. And so we really like it because it's super stable. As you can see down, it's not moving, and it's also at almost no backlash if you stretch the rope correctly. So yeah, that's our arm, and all this mechanism is built around this half-inch shaft that you can see, but it's screwed to the sides of our subplates. Use the original Go Build a Lifetime. We didn't see much problems with it, and we didn't really have much time to change it, but it's really good. And we have 3D printed bumpers that cover all of it. So I move to the intake. We use a dual wheel intake with flex wheels that are powered by an Axon micro servo with a 1:5:1 ratio that spins each wheel, and they are on moving arms, which can have like a rubber bear in here that closes them, so it can open and close on its own. But also there is another Axon micro servo that has this kind of teeth that pushes the arm, and on command we can open it to faster and better drop on the basket, and also for better intake. Yeah, so we also have lots of carbon fiber covering. This one is actually called Flipper Chunk. It's a kind of carbon fiber that is cheaper, and yeah, it's really cool, and really like this overall boxing. It looks very nice. So yeah, we have like our custom plates here, and yeah, that's what I have to talk about the robots.
In our software, the main algorithm is based on a final state machine. That means that it converts gamepad buttons into in-app objects called robot states. Additionally, every system has its own enum that represents its own system state. The goal of this algorithm is to go to one state using only one button. It means if, for example, if we press on A, it goes all the system go in one time into intake. Let's say that. That helps us a lot with one driver because it's way better and better for. So now I'll talk about our autonomous. For auto, we use Roadrunner 1.0, and we have an autonomous of 5 specimens and another autonomous of 4 samples.
So in our code, we also used some control. So in the control, we used PID on the motors of the telescope, the arm, and that's all. We also used motion magic like in the FFC. The motion magic is something we built. What it does, it's like makes the makes the arm run smoothly with like an with its acceleration and deceleration in the start and the end of the run, so it runs smoothly. And yeah, we also used feed forward, and we use like some parameters to overcome on physical forces like gravitation, like friction, and elastic forces in the telescope.
So I forgot to mention earlier, but we also have this mechanism, which is our climb. It attaches onto the bar, and when we close the arm, it also opens up like that, so it climbs on the center mass of the robot. So we have intake mode, which with this joystick I can move forward and backwards to intake correctly in the submersible. We have travel mode, which is where we move the state of we move the robot around in the field. Also in intake mode, we have, if we press again the button, I have vertical intake, so I can intake from above, I can move also with the joystick. And after intake, we can go to eye basket mode. Okay, here I can also move the telescope, and if you can see above, when I press the pleat, it opens up the claw like that. So travel mode again. And also we have eye chamber mode and wall intake mode for chamber. A nice button what we have is here, that when I press it, you can see the LEDs are blinking. What it means is that it changes the button that I have on my controller to different states. So now intake will be wall intake, and eye basket will be low basket, and eye chamber will be eye chamber but from the back of the robot, so we won't have to spin. And so yeah, you can see also, if you something nice that you can see here the capstan mechanism. When I press it, you can see the rollers moving and the rope moves around it. I did mention also that we have these rubber bands that counterweight the arm. And so yeah, we have around 14 plus states for the robot, just moved by this controller. I won't show you all because it's a lot, but it's very cool how one diver can control all the robot and every small subsystem, and yeah.
So another thing we have on a robot is like for the teler period. So we have some driving enhancements. So one of them is the intake override. So what you do, it's that the arm keeps its the same height that the driver chooses with the joystick. So you can show them. So as you can see, as the telescope gets longer, the arm raises its height, so it keeps on the same height. The intake is also changing its angle. It's pretty hard to see it right here, but it actually changes its angles, so it will always be on the same angle from the floor, and there it helps us.
And we achieve that with using trigonometric functions and linear interpretation.
Nice. I wish you the best of luck in the rest of the season, in the rest of the events, and see you soon.